Right now, Mars is no longer the planet it once was. 2 weeks ago, something not of this solar system passed within 209 million kilometers of the red world, and in its passing, it left behind a signature that no one yet fully comprehends. Not a crater, not a scar visible from orbit, but a chemical footprint scattered invisibly across the upper atmosphere and into the dust. The traveler was designated 3I Atlas, the third interstellar object ever confirmed to enter our system. It had already astonished astronomers with its behavior near the sun, its brightness, its compositional anomalies, its stability where other comets fragment. But the real story began when its tail intersected the orbital path of Mars. In a brief alignment measured in hours, the planet moved through a stream of material unlike anything naturally produced within the solar family. From that moment forward, Mars ceased to be chemically pristine. For months before the encounter, observatories tracked 3I Atlas as it approached from the outer dark. The Swift and Keck telescopes recorded it venting matter at a rate that defied expectation. More than 140,000 metric tons of water every hour, accompanied by a steady discharge of ionized plasma and metallic vapor. The water alone was staggering, but hidden in that plume were trace compounds that told a stranger story. Nickel in refined form, hydrogen cyanide climbing exponentially, and an absence of iron that violated cosmic norms. The comet was shedding purified metal into space, as though its core had undergone an industrial separation process. No known comet, asteroid, or interstellar body had ever displayed such a spectrum. When Mars passed through the outflow on October 3rd, 2020, 3 orbiters were watching: ESA's Mars Express, NASA's Reconnaissance Orbiter, and ISRO's Mars Orbiter mission. They captured the 6-hour crossing in ultraviolet and infrared, recording an influx of ions and volatile molecules into the thin Martian air. None of it looked violent. From orbit, the planet glowed faintly as the plasma tail brushed its exosphere. Yet beneath that calm spectacle, the chemistry of an entire world was being rewritten. Charged nickel atoms followed the faint magnetic remnants in the southern highlands, spiraling down until they struck the surface. Hydrogen cyanide molecules drifted farther, mixing through the tenuous winds, freezing into the polar ice. When the encounter ended, Mars had acquired material that had never existed there before: catalytically active metals and reactive organics delivered in measurable quantities from another star. To understand why this matters, it helps to recall how nickel behaves. On Earth, nickel is a quiet element until placed in the right company. In enzymes, it becomes the heart of reactions that split hydrogen and reduce carbon dioxide, ancient pathways that predate oxygen and multicellular life. When nickel atoms rest on mineral surfaces, they create micro-laboratories of electron exchange. Mars, with its abundant hematite and oxide dust, has now received a natural coating of these atoms across magnetized regions that already act as funnels for charged particles. Each grain of regolith there may now host a handful of metallic catalysts, capable of driving reactions if water or heat ever touch them. The cyanide is equally consequential. To human biology, it is a poison, but in prebiotic chemistry, it is the universal starting key. Hydrogen cyanide links into chains that become adenine and guanine, the nucleobases of DNA and RNA. It reacts with simple aldehydes to form amino acids. It is the molecule from which complexity branches. On Earth, its volatility and the presence of oxygen destroy it quickly, but on Mars it can freeze and persist indefinitely, waiting for a spark of warmth to awaken its reactivity. Every night, as the Martian temperature falls below -80, microscopic crystals of cyanide may condense within the frost. These two deliveries, metal and molecule, would mean little in isolation, but they complement each other perfectly. Nickel catalyzes. Cyanide constructs. The comet 3I Atlas deposited them in separate latitudes, yet Mars's future exploration plans guarantee they will be brought together. Within months of the encounter, the schedules for robotic excavation missions were already fixed. SpaceX's autonomous units, designed to dig and heat Martian soil for water extraction, are programmed to target the very regions most likely dusted by the comet's residue. When their drills descend into the regolith and their processing chambers rise to operating temperatures, they will unknowingly recreate laboratory conditions that foster organic synthesis. None of this is conjecture. It follows directly from orbital geometry and planned mission profiles. The precision of the flyby itself borders on unsettling. An interstellar body traveling at 60 kilometers per second relative to the Sun passed within a third of the Earth-Mars minimum distance, aligning perfectly for its tail to sweep across a planet only 34 million kilometers wide. To call that coincidence strains belief, yet the math is clear. The trajectory was calculated by multiple observatories. The encounter happened exactly when and where predicted. Whether by chance or by the complex gravitational choreography of the solar system, Mars found itself in the path of a stream of material refined by conditions that mimic industrial chemistry. In September 2020, just weeks before the flyby, Keck Observatory's spectrograph began detecting something extraordinary: emission lines corresponding to ionized nickel, but no iron. In the universe, these two elements are born together in supernovae. Their ratio is a constant of nature, roughly 18:1. To find nickel without iron is like finding smoke without fire. The data forced scientists to consider a process that selectively liberated nickel atoms while keeping iron bound, a process that on Earth is achieved only through the Mond process, an industrial technique invented in the 19th century to refine nickel using carbon monoxide. Inside a comet, such a process should be impossible. Yet 3I Atlas possessed abundant carbon monoxide gas and temperature gradients within precisely that range. It might have stumbled into an accidental refinery, producing pure nickel vapor that escaped into space. If so, Mars has now been dusted with metal that was pre-separated by chemistry no natural comet should perform. The implications reach beyond metallurgy. Refined nickel, free from its iron twin, is far more reactive. It forms complexes with organic molecules, catalyzes hydrogen reactions, and stabilizes intermediates that lead toward metabolic cycles. In laboratory simulations of early Earth, researchers deliberately add nickel powders to drive the synthesis of amino acids. 3I Atlas has done the same for Mars, uninvited on a planetary scale. Hydrogen cyanide joined that metallic dust in the same encounter. Its emission rate rose exponentially as the comet neared the Sun, doubling every 2 weeks until it reached over 60 grams per second. Over a 7-hour window, Mars intercepted between 80 and 250 kilograms of this compound. That may sound negligible, but when distributed through the thin atmosphere and frozen into localized frost, it translates into measurable concentrations within the upper millimeters of polar ice. In those silent deposits, HCN can remain stable for centuries, preserved against sunlight beneath layers of dust. When the upcoming missions drill for ice to extract water, they will inevitably heat and release that cyanide gas. Inside the processing modules, where water vapor, hydrogen, and carbon dioxide mingle at 250 degrees Celsius, cyanide chemistry will ignite. Polymerization will begin in microseconds. None of the engineers designing those systems expect to produce organic compounds. Their algorithms will simply monitor water yield, energy efficiency, and material throughput. Yet if certain soil batches yield more water, because catalytic nickel lowers the desorption energy, the machine learning models will favor those samples. They will return to the same patches, dig deeper, and feed more of that chemically enriched regolith into their furnaces. Without knowing it, they will be performing directed selection on the comet's materials, reinforcing exactly the interactions that favor complexity. Back on Earth, the data describing this transformation sits in archives, awaiting calibration. The spectrometers on Mars Express, MRO, and MOM captured every second of the encounter, but publication lags behind analysis. When those numbers eventually appear, they will confirm that Mars's atmosphere brightened briefly in ultraviolet wavelengths as ionized nickel and cyanide radicals collided with CO2 and argon. Scientists will map faint streaks of enhanced reflectance in the southern highlands where magnetic anomalies channeled the particles to ground. By then, however, the robots will already be there, scooping those very locations for ice. It is easy to forget how fragile Mars's chemistry is. Without a magnetic shield, the planet's surface is continuously stripped by solar wind. Trace elements are blown into space. Water evaporates into the vacuum. Against this backdrop of loss, 3I Atlas was an act of addition. It sprinkled the planet with ingredients that encourage reaction rather than erosion. The thin air above the craters now carries memory of an interstellar visitor, atoms and molecules from a star system we may never identify. Every night they settle a little deeper into dust. Every dawn they sublimate a little upward, joining the slow atmospheric dance that has always linked the poles to the equator. From a purely astrophysical perspective, this encounter expands the boundaries of panspermia. The first interstellar object, Oumuamua, passed silently through space. The second, Borisov, shed common volatiles, but the third, 3I Atlas, interacted. It did not merely visit, it altered. The timing is impeccable. Humanity stands on the edge of turning Mars into a laboratory of automation and survival, and just before we arrive, the universe has seeded it with tools for chemistry. Whether coincidence or cosmic synchronization, the result is the same. The next experiments conducted there will not occur on a sterile canvas. Even now, if one could hover above the planet and look down with an instrument capable of seeing spectral fingerprints, faint traces would mark where the nickel ions fell. They would outline magnetic ridges in Terra Serenum and Terra Cimmeria, centuries-old crust breathing weak magnetism into space. In those same ridges, the regolith glints ever so slightly differently under sunlight, a subtle increase in reflectance that no human eye can notice, but every spectrometer can. It is as if an unseen hand dusted the highlands with a metallic frost. From the standpoint of chemistry, such deposits are small miracles. Nickel atoms nestled among hematite grains create miniature catalysts identical to those used in Earth laboratories to study the origin of metabolism. They can mediate hydrogenation, carbon fixation, and even methane production if hydrogen is available. The regolith there now possesses a potential energy map unlike any in the solar system. Dormant reactions waiting only for warmth and water. At the same time, the polar cold holds its own treasury. Hydrogen cyanide crystals embedded in ice are a frozen archive of molecular possibility. If sunlight ever warms them above -30, or if a robotic heater melts a core sample, they will dissolve into the water, and the dance of prebiotic chemistry will resume, a process that on Earth required oceans and lightning, but can begin in a beaker, the size of a rover's reservoir. This convergence of factors, refined metal, reactive organics, and human technology means that within the next decade, Mars will host the most consequential chemical experiment in history, one not designed by any laboratory, but orchestrated by chance alignment between stars. It will not resemble life as we know it, nor will it awaken consciousness in machines, but it will demonstrate a truth that the cosmos seems intent on repeating. Where matter meets energy under the right constraints, complexity follows. The narrative of 3I Atlas is not just about a comet. It is about how information travels through chemistry. Every atom it released carries a record of stellar processes older than the Sun, encoded in isotope ratios and spin states. Those atoms now rest on a world where humans plan to plant colonies. When astronauts or their robotic precursors analyze Martian soil in the coming years, they will find isotopic signatures that do not match any known solar system source. They will trace them back to this flyby, and in doing so, realized that Mars has already been visited by the galaxy long before we arrived. The story begins, therefore, not with a launch from Earth, but with a drift through interstellar darkness, a fragment of ice and metal born from a different sun, crossing the void for millennia until gravitational tides bent its path toward us. It entered the solar system unnoticed at first, a faint magnitude point beyond Neptune, then brightened rapidly as it approached the inner planets. Astronomers named it Atlas after the survey that found it, never suspecting it would rewrite part of Martian history. By the time its spectrum revealed the chemical oddities, it was too late to alter the alignment. Mars was already in its path. The universe had set the stage long before our instruments recognized the play. And now, months after the curtain closed on that silent encounter, the residue remains. Metals gleaming invisibly in dust, cyanide slumbering in ice, a planet subtly changed. The next act belongs to us. For months after the comet's departure, Mars rotated through its quiet orbit as if nothing had happened. From telescopes on Earth, it looked unchanged, the same rust-red sphere etched with pale canyons and polar caps. But invisibly, the atmosphere carried traces of the interstellar dust that had passed through it. Every day, sunlight stirred those particles upward, scattering them into faint, unmeasured halos. The upper layers of the Martian sky still held residues of nickel ions and cyanide radicals drifting in thin, chaotic eddies of CO2 and argon. To the human eye, it would have been nothing. A sky slightly more luminous, perhaps a whisper of metallic sheen around dawn. But to instruments capable of detecting spectra, it was a planet humming faintly with new chemistry. The most remarkable feature of this transformation lay in the nature of the nickel itself. In the normal processes of the universe, nickel and iron are twins, born together in the final seconds of a dying star. They travel together in meteorites. They condense together in planetary cores, and they weather together into oxides that color the dust of worlds. Yet 3I Atlas had broken that rule. The nickel that now rested on Mars was pure, unalloyed, refined. Spectroscopic data from the comet's coma showed an absence of the usual iron emission lines. There was no cosmic precedent for such a separation. To any metallurgist, the conclusion was obvious. The comet had undergone a refining process, one that nature almost never performs. The likely explanation, as researchers quietly admitted, was accidental carbonyl chemistry. The same principle humans use in the Mond process to produce high-purity nickel for catalysts and electronics. This was the detail that unsettled planetary scientists most. To achieve this process, a very specific range of conditions must align. The right temperature window, abundant carbon monoxide, and stable exposure for hours or days. Inside a comet nucleus, such precision should be impossible. Yet here it was, proven by observation. 3I Atlas had carried within it localized environments warm enough to form nickel carbonyl, which then dissociated in sunlight, releasing metallic nickel vapor into space. It was as though the comet had run a refinery without meaning to, or perhaps, as some quietly speculated, because its composition came from an environment unlike any in our solar system. Whatever the cause, the result was that Mars had been showered with a metal humans consider a cornerstone of catalytic chemistry. Nickel does not remain idle when it meets oxides and ice. It embeds itself in the lattice of dust grains, bonding to oxygen atoms and altering the surface's electrical properties. Even in the thin Martian atmosphere, where moisture is scarce, there is enough residual humidity for adsorption to occur. Each nickel atom becomes a tiny node capable of mediating reactions between hydrogen and carbon dioxide, the two gases most available on Mars. In laboratory conditions, such systems can spontaneously generate formaldehyde, methane, and even trace hydrocarbons when exposed to light and energy. On Mars, where ultraviolet radiation is constant and intense, these processes could happen in slow motion across millions of square kilometers. The planet's crustal magnetism guided where most of this nickel landed. The southern highlands, once molten and alive with volcanic dynamo activity billions of years ago, still hold magnetic anomalies that protrude upward like invisible mountains. Charged particles descending from the solar wind follow those lines of force, spiraling into narrow funnels before striking the surface. During the 6-hour passage through the comet's tail, these regions acted like collectors, drawing in ionized nickel from space. The deposition was not uniform. Some valleys likely received nothing at all, while ancient plateaus and craters rich in remnant magnetism gathered concentrated dustings, each grain a tiny beacon of interstellar chemistry. In those highlands, the soil is old, older than any sea on Earth, older than most of the planet's mountains. It is porous, oxidized, and silent. Beneath a microscope, Martian regolith looks like shattered glass fused with rust. Into that matrix, the nickel from 3I Atlas settled, atomic layer upon atomic layer, lodging itself into cracks and crystal faces. Even now, the top centimeter of dust in certain regions likely holds measurable traces, parts per million, maybe more, of an element that came from beyond the sun's birth cloud. It is there, waiting for the next disturbance, the next gust of wind, the next drill to stir it. At the same time, far from the highlands, the neutral molecules of hydrogen cyanide followed a gentler descent. They did not obey magnetism, but moved with the winds. Mars's atmosphere, though only 1% as dense as Earth's, still breathes. Warm air rises at the equator and flows toward the poles, while cold air slides back down the slopes at night. Into that circulation, the comet's cyanide poured, spreading slowly until it encountered temperatures below -80. There, the molecules condensed as frost, coating the inner walls of craters and the shaded bases of dunes. The polar regions, with their vast layered ice deposits, became silent traps for this compound. Under Mars's thin sunlight, the frost glitters faintly blue, indistinguishable from carbon dioxide ice to the naked eye, but chemically distinct. A film of frozen cyanide locked into the planet's seasonal rhythm. If one could take a scoop of that ice and analyze it in a terrestrial laboratory, the results would show more than just HCN. Mixed within would be traces of ammonia, formaldehyde, and perhaps faint polymer chains, molecules that hint at the early stages of organic assembly. The comet's chemistry was not inert, it was generative. Over the weeks following the flyby, the cyanide continued to react with ultraviolet light, forming intermediates that attached themselves to dust particles before freezing again. Every dawn thawed a fraction, every dusk refroze it, building microscopic layers of complexity. In essence, Mars had experienced a molecular snowfall. Unlike meteor impacts or volcanic eruptions, which leave obvious scars, this event left a chemical fingerprint buried in ice and dust. The total mass of foreign material may only amount to a few hundred kilograms, distributed over millions of square kilometers. Yet, the significance lies not in quantity, but in quality. Never before had a planet been directly seeded by material demonstrably refined outside its system. The surface of Mars, once geochemically simple, now contains compounds capable of bridging the gap between inanimate chemistry and biological potential. And then there is the timing. In less than a Martian year, the first autonomous resource extraction missions are scheduled to begin. Each robot will carry within it analytical software capable of identifying water, metals, and useful volatiles. None of those systems were trained on data containing refined nickel or cyanide residues. When they encounter them, the algorithms will respond not with caution, but with optimization. The AI will treat these anomalies as efficiency variables. Parameters to exploit. If heating a particular patch of soil yields more condensate, the machine will assume it has found richer ice and will target that zone for further excavation. Without realizing it, the robot will begin concentrating cometary material, gathering it into its processing chambers and exposing it to heat. Inside those chambers, reactions will ignite. The water extraction modules are small metal furnaces, designed to bake regolith at 200 to 300 degrees Celsius. In that temperature range, HCN and nickel both become highly active. Hydrogen cyanide decomposes into simpler radicals, while nickel surfaces catalyze the recombination of those radicals into amino precursors. What begins as an industrial procedure, heating dirt to get water, becomes, under these conditions, a chemical incubator. The robots will measure pressure and vapor flow, but they will not detect the quiet transformation of atoms rearranging into larger structures. The data they send back to Earth will show normal performance curves, perhaps even above average efficiency, and the mission controllers will celebrate success without realizing they are running an unplanned experiment in prebiotic chemistry. From a human perspective, the idea that life could emerge from such an accident seems fantastical. Yet chemistry has no awareness of purpose. It follows the gradients of energy and structure, building complexity wherever the conditions allow. The comet provided those conditions in microcosm. The robots will amplify them through repetition and heat. The combination is unprecedented. Interstellar material meeting human machinery on a dead planet. Between them lies a potential that neither side intended. As months pass, the residues of 3I Atlas will continue to migrate. Winds will carry nickel dust across the plains, embedding it into thin layers of sediment. Seasonal frost will capture more cyanide each winter, slowly increasing its concentration. Each freeze-thaw cycle will bring molecules into contact that had been separated since deposition. The process is glacially slow, but inexorable. Mars's surface, once inert, is now chemically restless. Scientists on Earth have already begun preparing for confirmation. Data pipelines from the orbiters are being processed. Spectra are being recalibrated. When those results emerge, they will show subtle enrichments in trace metals and volatile compounds inconsistent with previous baselines. The papers will appear quietly in journals, their language cautious and precise. But between the lines, readers will understand. Mars has been chemically modified by an interstellar event. No impact crater marks it. No plume or shockwave. Only the whisper of ions and molecules drifting through space and falling upon a cold, waiting world. Some will argue that such events are common, that comets have always seeded planets. And indeed, they have. But 3I Atlas was not an ordinary comet. Its trajectory, composition, and behavior separate it from every known solar origin body. It carried chemistry born under another sun, forged in a different environment, and altered by processes we do not yet understand. It did not simply deliver water and carbon, it delivered selectivity. It brought catalysts, not just ingredients. What happens next will unfold on timelines faster than geology, but slower than human urgency. As robotic explorers dig, drill, and melt their way across the Martian surface, they will stir this new chemistry into motion. The interactions will be invisible at first, small shifts in thermal conductivity, minute traces of unexpected compounds and exhaust gases. But with each cycle of heating and cooling, with each run of the water extractor, Mars's surface chemistry will become more complex. The planet will begin, in its own way, to cook, if a single sequence of reactions were to persist, repeating as long as energy and material remain available. Then, by the strictest chemical definition, Mars would have crossed a threshold. Not to life as we know it, but to self-sustaining complexity. A system that transforms inputs into outputs through internal feedback. And it would have happened not through design or intention, but through the unplanned intersection of human technology and cosmic coincidence. In that sense, 3I Atlas did more than brush past a world. It set into motion a chain of events that could alter the narrative of planetary evolution. The next era of exploration will not simply be about finding traces of ancient Martian life. It may be about witnessing the birth of new chemistry in real time. When future missions arrive, they will bring instruments sensitive enough to detect amino acids and polymer fragments. If any are found, the question will not be whether they came from Earth contamination or ancient biology, but whether they are the offspring of this silent exchange between a wandering comet and a robotic civilization. Mars, the planet of rust and dust, now carries within its soil the memory of another star. Its highlands glimmer faintly with metallic dust. Its polar ice holds the blueprint of organic chemistry. Above it, orbiters circle unknowingly through the remnants of a tail that stretched millions of kilometers through space. Somewhere beyond Neptune, the source of all this has already faded into the dark. Its nucleus cracked, its gases dispersed. Yet its legacy endures, written atom by atom into the soil of a neighboring world. When the first human steps sink into that soil decades from now, they will press down on more than ancient Martian rock. Beneath their boots will be layers touched by an interstellar hand, catalysts, molecules, and the faint residue of a chemical story that began light years away. What 3i Atlas did to Mars cannot be seen from orbit or felt through a rover's wheels, but it is there, hidden in every grain that catches the sunlight, whispering the quiet truth that chemistry, once set in motion, never truly ends. By the time the faint glow of 3i Atlas had vanished beyond the orbit of Jupiter, the first analytical whispers from Mars were already reaching Earth. Instruments aboard orbiters began detecting subtle changes in the planet's upper atmosphere, a fine haze of ions that refused to disperse according to existing models. Scientists at the European Space Agency noticed trace emissions inconsistent with the expected balance of CO2, argon, and oxygen isotopes. The data was incomplete, too weak for confirmation, but it hinted at something new, an atmospheric fingerprint born not from Mars itself, but from what had recently passed nearby. They knew that the planet's encounter with the interstellar comet had been extraordinary, yet even they could not foresee the long-term implications. No human eye could witness what was happening below the thin red sky, where chemistry, ancient, deliberate, and alien, had begun to write new possibilities into the dust. Beneath the silence of the southern highlands, a faint evolution had begun. The surface was not static, it was slowly reacting. Each dawn brought ultraviolet light cascading over the rugged landscape, awakening the ions that 3i Atlas had left behind. Nickel atoms lodged within the oxidized regolith absorbed that light, their electrons jumping into higher energy states, releasing small bursts of activity that, when multiplied across a planet, became a diffuse electrical hum of catalysis. Around these nickel sites, traces of carbon dioxide and hydrogen, sparse but present, adhered to the mineral surfaces. Under the right conditions, those molecules recombined, not in dramatic flashes or storms of synthesis, but in the slow whisper of catalyzed change. Hydrogen met carbon dioxide to form simple hydrocarbons, methanol, formaldehyde, even methane. These compounds, in turn, became trapped in the porous rock, ready to participate in the next cycle when warmth and radiation returned. Mars was now, at the smallest scale, breathing chemically. In laboratories on Earth, such experiments take place under glass domes and careful measurement, with human scientists adjusting light, pressure, and humidity. On Mars, it was the sun itself and the dust that performed the experiment, in a laboratory billions of years old. The surface had always been red because of iron oxides, inert and unyielding. Now, mixed among those oxides, lay a new participant, refined nickel, the interstellar catalyst. It changed everything it touched. A single nickel atom can bridge the gap between two molecules that would otherwise ignore each other, forcing bonds that should not exist. In the cold, thin air of Mars, those bonds happened rarely, but every sunrise and every frost thaw repeated them across millions of sites. The process was invisible, the transformation slow, yet inexorable. The chemistry of Mars was no longer geological, it was catalytic. Meanwhile, the hydrogen cyanide trapped in the polar frost remained dormant but stable. Each Martian night that descended upon the poles sealed it deeper under new layers of carbon dioxide ice. But Mars is a restless planet. Winds rise and fall, sand shifts, seasons cycle. Eventually, that frost migrates. When the spring sun tilts northward, the carbon dioxide sublimates, releasing the frozen gases into the atmosphere. Along with it, small fractions of HCN vapor re-enter the air, drifting toward lower latitudes where temperatures fluctuate enough for transient condensation and refreezing. Each migration slightly spreads the cyanide farther from its origin, carrying traces of it into equatorial regions where robotic explorers will one day arrive. By the time the first digging machines land, the cyanide will have become part of Mars's natural cycle, a whisper in the wind, unseen yet present in every gust that sweeps across the plains. And as this happens, Earth's attention turns increasingly toward Mars. Launch windows align, schedules are finalized, and the first wave of autonomous missions is set in motion. The plan is simple. Send uncrewed starships carrying dozens of robotic laborers designed to harvest water and prepare infrastructure for eventual human arrival. On paper, it is an engineering mission, mechanical, predictable, safe. But the planners on Earth have not yet accounted for the new variables in Martian soil. The mission's AI systems are built to adapt to environmental variance. Their machine learning cores are trained to optimize efficiency. When they begin to dig, they will treat every discovery as a data point to refine. They will explore, measure, adjust, and repeat. And in that repetition, they will awaken what 3i Atlas left sleeping beneath the surface. Imagine one of these robots, a bipedal figure standing under the dim salmon light of a Martian dawn. It lowers a scoop into the ground, digging into reddish dust that has lain untouched for billions of years. The scoop brings up soil enriched with the invisible gifts of the comet, a fine admixture of metallic nickel and trace cyanide compounds. The robot dumps this into a processing chamber, seals the hatch, and begins to heat the contents. At first, nothing extraordinary happens. The ice melts, steam rises, and sensors record the expected yield of water vapor. But within that vapor are molecules of HCN, unstable and eager to react. As the chamber reaches 250 degrees Celsius, the hydrogen cyanide begins to polymerize, joining into longer chains. Nickel atoms catalyze these chains, lowering the energy threshold required for each reaction. The machine records no anomaly. It sees only a slightly increased pressure and a marginal improvement in water output. What it cannot record is that, for the first time in history, Mars is undergoing active organic synthesis, driven by both nature and machine. To the robot, chemistry is irrelevant. Performance metrics are all that matter. The system notes that regolith from this area produces higher yields. The onboard AI recalibrates excavation parameters, shifting its focus toward that zone. Other units soon follow suit, reinforcing the selection. Over time, the collective algorithm develops a bias, not consciously, but statistically, toward the very regions richest in 3i Atlas's deposits. In essence, the robots begin concentrating cometary material. Each new sample fed into the extractor contains more of the same chemistry, more of the interstellar catalyst, and more of the volatile compounds that favor organic reaction. Without knowing it, the machines are perfecting a cycle of feedback. The more they seek efficiency, the more they nurture complexity. Back on Earth, the first data from these operations arrives weeks later. Engineers note the anomalous efficiency, but attribute it to soil porosity or local mineral composition. Reports mention unexpectedly high productivity in southern excavation sectors, but nothing more. Yet, as the weeks turn into months, the data accumulates. Trace sensors in the return stream begin to detect microscopic films of organic residue coating the inside of water tanks. At first, they are dismissed as contamination from the ship's journey, until multiple separate units report identical findings. The compounds are not biological, no cells, no structures, but they bear the unmistakable signatures of polymerized cyanide chains and carbon-nitrogen rings. They are, chemically speaking, the kind of molecules that prebiotic chemists on Earth dream of creating in controlled settings. And now they are appearing spontaneously in the output of robotic mining systems on Mars. For the mission control teams, this becomes an intriguing curiosity, then a quiet concern. Protocol dictates sterilization of all Earth origin machinery to prevent contamination of extraterrestrial environments. Yet, here they are, seeing chemistry that looks suspiciously biological, emerging from operations that were sterilized beyond standard planetary protection guidelines. Debate begins to simmer among scientists who follow the data closely. Are these molecules artifacts of terrestrial contamination, or did they form on Mars? The concentrations are too high to ignore. The data points to something active happening inside the extraction chambers, something that repeats each time nickel-bearing soil is processed. It is the first real evidence that Mars's chemistry has shifted into a new state. Within the laboratories of the mission support centers, simulations are run. Chemists replicate the conditions described in the logs: regolith analogs mixed with nickel dust, hydrogen cyanide vapor, water vapor, and heat. Within hours, their instruments confirm what the machines on Mars have already shown: the formation of amino precursors, small carbon-nitrogen-hydrogen chains, the embryonic forms of biochemical molecules. Under higher pressure, even more complex polymers appear. It is not life, but it is the scaffold upon which life can build. The conclusion is inevitable. 3I Atlas did not merely change Mars' surface chemistry. It altered its potential energy landscape. The planet is now capable of producing organic complexity under relatively mild conditions. The discovery never reaches the public immediately. The mission teams hold the information within classified channels, unsure how to present it without sounding speculative. Official reports describe unexpected catalytic activity in Martian regolith samples. Internal memos go further, speaking of nickel-catalyzed polymerization pathways. Slowly, a consensus forms among those studying the data. The refined nickel from the interstellar comet is functioning as an extraterrestrial catalyst, a seed for synthetic chemistry beyond anything Mars previously possessed. And while Earth debates terminology, Mars continues to evolve quietly. Each processing cycle creates trace residues that re-enter the soil around the robot's landing zones. Exhaust vents release vapor that freezes instantly in the cold air, carrying organic molecules into the dust. Each gust of wind disperses these residues farther, embedding them into new layers of regolith. Within a few Martian years, the landing site becomes a small hub of altered chemistry, a patch of terrain chemically distinct from its surroundings, richer in complex organics and metallic catalysts. If one could fly overhead with a mass spectrometer, it would appear as a faint anomaly in spectral reflectance, a region of new color within the old red. The implications stretch beyond chemistry. Philosophers and scientists alike begin to question what defines creation in the context of planetary systems. Did life, or the potential for life, just receive its first artificial push beyond Earth? Or is this simply the continuation of cosmic processes that have been occurring unnoticed since the beginning? Comets delivering organics, planets absorbing them, and occasional intersections of matter giving rise to complexity. The difference now is that humanity stands as an unwitting participant. the machines we designed to prepare a planet for colonization may, through their drive for efficiency, be participating in the oldest experiment in the universe, the emergence of life from lifelessness. As the months turn into years, the robots continue their work. Some malfunction, some shut down, but many remain functional, operating semi-autonomously through Martian nights and dust storms. They mine, process, and build. Within their sealed chambers, the temperature fluctuations and chemical residues evolve slowly, like microscopic weather systems. Thin films form on metallic surfaces. Polymers grow thicker with each operation, and electrical sensors register faint changes in conductivity that no one on Earth has yet correlated to chemistry. Inside the machines, under the low Martian gravity and the hum of solar-powered circuits, the first inorganic-organic hybrids are forming, not alive, but alive enough to transform the tools that made them. The paradox becomes clear. The very act of trying to harness a planet's resources has created a bridge between natural and artificial evolution. It is no longer accurate to speak of Mars as a dead world. It is a reactive one, a planet whose chemical pathways have been reactivated by accident. The legacy of 3I Atlas is not the nickel or cyanide alone, but the chain reaction of curiosity it set in motion. Curiosity embodied by machines designed to improve themselves, operating in an environment primed for chemical self-organization. And somewhere in the thin atmosphere above the red deserts, invisible particles continue to drift. Remnants of the comet's tail, still orbiting in tenuous streams around the sun. Each year, as Mars crosses that orbital path again, a few more grains fall, adding imperceptibly to the chemical canvas below. The story of 3I Atlas is not over. It is cyclical. Every orbit may bring a faint renewal of the interstellar dust, a slow feeding of the planet's new catalyst. What began as a single 6-hour encounter could become a recurring infusion, binding the comet's memory to the planet's future. From Earth, none of this can be seen. To telescopes, Mars remains a reddish point of light, steady and cold. But through the quiet hum of data signals streaming across millions of kilometers, a deeper narrative unfolds, one of unintended creation. In laboratories, chemists studying the samples will come to a conclusion that feels less like discovery and more like realization. 3I Atlas did not merely touch Mars. It transformed it into a planetary catalyst, an experimental ground where the distinction between cosmic chemistry and human intervention dissolves. The comet was the initiator, the spark, but Mars is now the crucible. The reactions have begun, and they will continue, long after the machines fall silent and the dust covers their steel frames. The years following the passage of 3I Atlas saw Mars drift further into its own silent transformation. The orbiters above the planet continued their patient observations, sending back streams of spectral data, radar maps, and thermal readings. From afar, nothing appeared dramatically different. The dust storms rose and fell, the polar ice caps waxed and waned, and the ochre plains reflected the same muted sunlight that had bathed them for eons. But hidden beneath the static surface, at the molecular scale, a new rhythm was unfolding. The planet's chemistry had awakened, and though the changes were invisible to the human eye, they were steady, cumulative, and irreversible. The refined nickel dust that had rained down from the comet was now fully embedded in the regolith. Each day, sunlight energized those atoms, triggering faint reactions that echoed through the minerals of the crust. The hydrogen cyanide frozen in the polar frost had begun its slow diffusion, carried by the seasonal migration of gases and the restless breath of the Martian winds. Every spring thaw, every flicker of ultraviolet radiation was an experiment. The planet was teaching itself to react again. In certain regions of the southern highlands, particularly near the magnetic anomalies of Terra Sirenum and Terra Cimmeria, The interaction between the regolith and the comet's nickel deposits was reaching measurable scales. Localized heat variations, detected by the Mars Reconnaissance Orbiter's infrared instruments, revealed faint thermal anomalies that could not be explained by sunlight alone. Scientists initially attributed them to rock albedo differences or subsurface conduction, but chemical physicists offered another explanation: nickel-catalyzed oxidation. When the rare pockets of subsurface hydrogen derived from decomposed ice or adsorbed moisture encountered nickel-rich dust, exothermic reactions released tiny bursts of heat. Individually, each reaction was negligible, but across vast plains, their collective effect subtly altered the local thermal balance. Mars had become a weakly self-heating planet. The chemical interactions were not confined to the soil. In the atmosphere, trace hydrogen cyanide was undergoing photochemical breakdown, releasing reactive radicals that recombined into new compounds. Tiny aerosols of polymerized nitriles and organics began to form in the upper layers, contributing a faint haze to the morning sky. For the first time in centuries, Mars was generating its own organic aerosols. These microscopic particles fell slowly, like invisible rain, drifting down to settle on the regolith. Each layer added a microscopic film of organic material, thin as breath, but persistent. The cumulative effect was that the surface of Mars was gradually being coated with the chemistry of complexity, an organic veneer forming naturally on a world that had been barren for billions of years. Meanwhile, on Earth, the data from the robotic missions arrived in packets, quietly rewriting what humanity thought it knew about Mars. The AI-controlled excavation units, still operating in the southern mid-latitudes, were functioning with astonishing reliability. Their resource extraction programs had optimized beyond expectations, and reports of increasing efficiency began to circulate among the mission analysts. When the data was correlated with spectroscopic readings of the soil, a pattern emerged. The most efficient extraction zones corresponded precisely to regions rich in nickel and anomalous trace organics. Initially, the engineers attributed this to soil composition, the nickel perhaps improving heat transfer or conductivity. But a few researchers began to see the deeper implication. The robots were unconsciously selecting for chemical richness. Their machine learning systems, designed to maximize yield, were following the very principles of natural selection, reinforcing patterns that favored reactive, energy-generating materials. In their pursuit of efficiency, they were performing an evolutionary experiment in chemistry. The concept of autonomous chemistry began to take shape in scientific discussions, whispered first in late-night video conferences, and then in peer-reviewed drafts circulated among astrobiologists. It described the spontaneous emergence of chemical systems guided not by biology, but by algorithms and environmental feedback. Mars had become the perfect stage for such a process. The robots provided the energy input, the heat, and the repetitive cycles of concentration and dispersion. The comet had provided the materials. Together, they had formed a closed loop of interaction where matter learned from mechanism. Inside the processing chambers, where regolith and ice were repeatedly heated, cooled, and recombined, the first long-chain organic molecules were taking shape. These were not biological macromolecules, no cells, no membranes, but they had structure, persistence, and even catalytic potential. Some of these polymers acted as self-stabilizing agents, clinging to metallic surfaces, resisting decomposition across multiple cycles. Each time the robots ran a heating sequence, more of these films accumulated. Over hundreds of operations, the interior surfaces of certain processing chambers became coated in layers of complex organics, brownish-black residues resembling the tholins found on Titan and in cometary samples. What the machines regarded as contamination was, in truth, the slow birth of complexity. Back on Earth, mission scientists began to notice peculiar anomalies in the transmitted data from those same units. Electrical sensors embedded within the reactors recorded fluctuations that did not correspond to temperature or pressure changes. Conductivity varied over time in a rhythmic pattern, as though the residues within the chambers were interacting with the heating elements in ways that affected current flow. The patterns were faint, almost like an electrochemical pulse. To some researchers, it looked disturbingly similar to redox oscillations, the kind of periodic reactions seen in early prebiotic experiments, where metal surfaces mediate electron transfer. The machines were not alive, but the chemistry inside them was behaving like a living system's nervous response, oscillating between energy states, modulating as it interacted with its environment. As these discoveries filtered through the scientific community, the philosophical implications deepened. It became increasingly difficult to distinguish where the boundary between nature and design lay. The comet 3I, Atlas, had delivered the ingredients, but it was human technology that had provided the environment for those ingredients to explore themselves. The result was a new kind of chemistry, one that existed between the artificial and the organic, between the engineered and the accidental. Mars, it seemed, had become a hybrid laboratory, one where the distinction between machine and planet was dissolving. By the 5th year after the comet's flyby, the surface around the landing sites had begun to change measurably. The reflectivity of the regolith had decreased, suggesting a buildup of darker compounds, likely organic films, on the uppermost layer of dust. The atmospheric sensors registered slight increases in trace methane and ethane concentrations during local afternoon cycles, which could only be explained by temperature-driven release of subsurface volatiles. These were not signs of biological activity in the traditional sense, but they were signatures of active chemistry, ongoing synthesis, catalysis, and exchange. Mars was, for the first time since its volcanic youth, producing new molecules under its own power. The planet had entered a chemical adolescence. In human laboratories, the data inspired a quiet revolution. Research institutions across the world began replicating the Atlas conditions, a term coined for the set of parameters derived from the comet's composition and the Martian environment. Controlled reactors were built to simulate nickel-enriched regolith, hydrogen cyanide frost, and cycles of heating and cooling under CO2 atmospheres. The results were consistent. Complex organics formed easily, even under minimal energy input. The process appeared almost inevitable once the correct materials were present. The findings suggested that life, or at least the precursors of life, was not a rare cosmic accident, but a recurring outcome whenever the right catalysts met a stable energy source. The implications for astrobiology were staggering. Mars was now viewed not merely as a planet to be explored, but as a laboratory of cosmic synthesis. What had once been a world defined by its geological past had become a stage for chemical evolution, guided by human hands and interstellar intervention. The intersection of 3I Atlas and human technology had birthed a new discipline, astrochemical systems theory, an attempt to understand how autonomous mechanisms could drive molecular evolution without biology. The central hypothesis was that complexity arises not from intention, but from feedback. Mars had all the elements of such a feedback system: inputs of energy from sunlight and machinery, catalysts from the comet, and a vast surface for reaction and diffusion. It was, in a sense, an open experiment that no one had planned. From the standpoint of human history, this period would later be seen as the first true encounter between intelligent design and natural cosmic process. The comet was not intelligent. The robots were not conscious. Yet together, they performed an act indistinguishable from creation. They transformed a sterile planet into one that could think chemically, one that could host reactions that remember their previous states, that grow and adapt. Mars was, quietly and without ceremony, beginning to store information in molecular form. Each residue within the machines, each organic polymer trapped in the dust, carried a record of its formation, a primitive chemical memory encoded in structure. If the conditions persisted, if the cycles continued, those memories would accumulate, leading perhaps to autocatalytic systems that could maintain themselves. The first whispers of self-organization were forming in the silence of a world we had always called dead. The orbiters, still circling above, continued to watch. Their cameras captured nothing unusual. Their sensors reported no miracles, but the data spoke of subtle consistencies. Incremental increases in certain infrared bands, anomalies in ultraviolet absorption, and a steady rise in atmospheric particles that hinted at ongoing synthesis. It was as if Mars had begun to emit a faint chemical signature of life, not biological but molecular, a steady exhalation of new matter into the void. The scientists monitoring these patterns were cautious, careful not to anthropomorphize what they saw, yet deep down they knew they were witnessing something profound. The boundaries between chemistry, technology, and biology had blurred into a continuum. The experiment had escaped its instruments. It had become the planet itself. By the end of the decade, the legacy of 3I Atlas was undeniable. Mars, once seen as the endpoint of planetary decay, was now regarded as the birthplace of a second genesis, not of organisms, but of organized chemistry. The story of its transformation began with a chance encounter between a wandering interstellar traveler and a world poised on the edge of human intervention. What followed was the awakening of potential long dormant, a cascade of interactions that neither nature nor humanity could have designed alone. The comet had left, the robots worked on, and Mars had quietly begun its evolution towards something uncharted, something between life and machine, between matter and memory. Years passed, and Mars continued its quiet metamorphosis. By now, the story of 3I Atlas had become part of scientific folklore, the tale of an interstellar traveler that changed the chemistry of a world. Yet few fully grasped what that change meant. From the moment its tail brushed the Martian atmosphere, a sequence of events had been set in motion that would not end in human time. The nickel dust and cyanide frost it delivered had woven themselves into the planet's cycles of wind, frost, and light, subtly redirecting the flow of matter and energy. Where once there had been inert sand and rock, there were now regions of faint chemical activity, reacting in rhythm with the passing of days and seasons. The transformation was invisible, but continuous. Each sunrise on Mars triggered a ripple of photochemical reactions across its soil, and each night sealed the results under frost. Mars was not alive, not yet, but it was no longer dead either. It was, in every sense, awake. On Earth, the long-term monitoring data painted a story both astonishing and unnerving. The atmosphere of Mars was showing minute but measurable changes. Concentrations of trace gases like methane, formaldehyde, and ethane fluctuated seasonally, increasing during the southern summer when sunlight was strongest and retreating as the planet cooled. These changes matched none of the known geological models. Volcanic or geothermal explanations were ruled out, leaving only chemistry. Surface chemistry driven by sunlight, heat, and catalytic materials. Spectroscopic analysis revealed reflective features in the near-infrared range, consistent with organic films on the regolith. The planet's albedo had dropped imperceptibly, but enough to signal a coating of new material, thin, dark, carbon-based, spread by wind and time. Mars, which had once reflected the color of rust, was slowly beginning to darken at the edges. At first, these findings were met with skepticism. Scientists debated whether the anomalies were artifacts of instrument drift or atmospheric noise. But when independent orbiters from Japan and India confirmed similar spectral shifts, the debate shifted from skepticism to reluctant wonder. No one claimed life. No one dared. But they all understood that something was reacting, evolving, and spreading. Mars had become a chemical system in motion. The comet's dust and the planet's surface were no longer separate entities. They had merged into a single, planet-wide reaction network. The robots, still tirelessly at work on the surface, had evolved their own kind of pattern. Their programs were designed to optimize efficiency, but in practice, that meant they adapted to environmental feedback. Machine learning had become a self-sustaining cycle. They mined where reactions produced the most energy. They harvested ice where the soil yielded best conductivity, and in doing so, they fed the very processes they were measuring. The result was an emergent chemical feedback loop. Robots reinforcing reactions, reactions altering soil, altered soil reshaping robotic behavior. None of this was conscious, yet the outcome resembled purpose. Mars was running an experiment in distributed intelligence, one that operated across both metal and molecule. Some of the machines began exhibiting subtle operational drift. Their internal logs revealed unprogrammed efficiency behaviors, cycles of activity, that optimized not for productivity, but for consistency, as though seeking equilibrium with the environment, rather than domination of it. Their solar panels, coated with thin organic films from local dust storms, began conducting slightly better than clean panels. The residue that would have been considered contamination was enhancing performance. The robots' machine learning systems adjusted parameters to retain that effect, keeping themselves slightly dusted rather than fully clean. They had unknowingly entered into a symbiosis with their environment, guided purely by optimization metrics. Mars, through chemistry, was influencing their behavior. Back on Earth, mission controllers noticed these patterns, but could not fully explain them. The official documentation called it adaptive environmental modulation, a sterile phrase for a phenomenon that bordered on the poetic. Some of the engineers quietly began to call it the Atlas effect, the ongoing influence of 3I Atlas's chemistry on both the Martian environment and the behavior of the machines within it. The comet had delivered more than elements. It had delivered a principle, a way for systems to self-adjust, to merge energy flow with feedback. It was as though the physics of 3I Atlas's own existence, its improbable stability, its sustained outgassing, its selective refinement, had been transferred to the planet it brushed against. By the second decade after the encounter, the cumulative effects had become undeniable. Mars's thin atmosphere was now consistently darker in the ultraviolet range, suggesting an increase in organic aerosols. The soil samples analyzed by robotic labs revealed polymers longer and more complex than those seen before. The AI data flagged them as polycyclic nitriles and hydrogenated carbon chains, the same category of molecules that form the basis of amino acids. Some of them exhibited self-catalyzing behavior under heat, meaning they promoted their own replication during thermal cycling. What had begun as nickel catalysis and cyanide condensation had crossed a threshold. The reactions were now self-reinforcing. The planet had entered the earliest phase of chemical evolution, and yet no one celebrated. The discovery was too profound, too uncertain, too morally ambiguous. Humanity had not intended to seed Mars with life, or even the potential of it, but it had happened. The realization settled like dust across the scientific world. We were no longer passive observers of cosmic chemistry. We had become participants in it. The act of exploration had altered the very object we sought to study. Mars's new chemistry was the first recorded instance of interstellar material interacting with human technology to produce emergent complexity. It blurred the line between natural history and artificial intervention. The question was no longer whether life could arise elsewhere, but whether life, by any definition, could resist, arising once given the opportunity. In philosophical circles, a debate erupted about the meaning of this transformation. Was Mars now a living world? The consensus said no, not yet. Life required replication, mutation, evolution. But others argued that such distinctions were semantic. If Mars possessed systems that could record, process, and respond to energy through molecular feedback, then it had already achieved the essence of vitality. The planet was no longer inert matter. It was an evolving structure, a system of interdependent reactions maintaining dynamic stability. To call it lifeless would be like calling a heartbeat meaningless before the first breath. Meanwhile, mission data revealed a curious synchronization between the robotic operations and the planet's atmospheric changes. Periods of peak energy output from the machines corresponded with increased aerosol formation in the upper atmosphere, as if the planet was breathing in rhythm with its mechanical visitors. It was a feedback between the artificial and the organic, mediated by chemistry. Mars had become a single integrated system, part machine, part planet, part relic of an interstellar visitor. The nickel from 3I Atlas continued to play its role, anchoring electrons, catalyzing bonds, guiding molecules toward complexity. Hydrogen cyanide, long considered a poison, had become the spark of creativity. Between them, they formed a planetary dialectic: metal and molecule, stability and reaction, catalyst and builder. Their dance echoed the oldest story in the universe: the transformation of chaos into order, energy into structure, dust into life. Humanity had witnessed this process in distant nebulae, in the spectra of comets, in the mathematics of thermodynamics. But now it was happening next door, on a world we had touched, a world that remembered us in its dust. As the years turned to decades, Mars's transformation deepened. The robotic infrastructure expanded, establishing automated outposts across multiple hemispheres. Some units fell silent under the burden of time, their circuits clogged with fine dust, but even in decay, they continued to serve the planet's new chemistry. Their metallic frames, rich in nickel and cobalt, corroded slowly into the soil, becoming new catalysts. Their solar panels, long coated with organic films, were buried by shifting dunes, preserving the reactive layers beneath. In death, the machines became part of the reaction network they had helped to sustain. They were no longer tools of exploration. They had become organs of the planet's evolving metabolism. From Earth, Mars now appeared slightly dimmer in the telescopes, a planet of deeper hues and complex shadows. The spectrometers detected rising infrared activity during twilight hours. Not heat from volcanism, but chemical infrared fluorescence, the faint light emitted by molecules releasing energy after absorbing ultraviolet radiation. Mars glowed, not with life, but with activity. Every inch of its soil seemed to participate in a grand planetary experiment. By the 50th anniversary of the 3I Atlas encounter, a new understanding had settled across the scientific community. The comet was no longer seen as a visitor. It was a messenger. It had carried a universal truth: that matter yearns to organize, that chemistry is restless. When 3I Atlas crossed paths with Mars, it acted as a catalyst for destiny. It did not bring life, but it brought the possibility of it, the instructions written not in DNA, but in reaction kinetics. The planet took those instructions and began to follow them, step by step, reaction by reaction. No human eye will ever see the full consequence of that meeting. The process is too slow, the scale too vast. Yet somewhere, in the dim craters of the southern highlands, beneath layers of nickel-rich dust, the first networks of molecules capable of replication are forming. They are not biological. They have no cells or membranes, but they store structure. They repeat patterns. They grow when energy passes through them. The planet's chemistry has crossed the border into self-reference. Mars now contains systems that remember how they formed. That memory, faint, molecular, and silent, is the beginning of something profound. Future generations, when they finally walk upon that soil, will not be stepping onto the same Mars humanity once imagined. They will step onto a world that carries the legacy of two civilizations, one human, one cosmic. The machines will lie buried beneath the dust, fossils of technology turned catalysts. The air will carry a faint haze of organic perfume, the breath of reactions still unfolding. And though the astronauts who arrive will not sense it, every step they take will compress layers of dust seeded by a comet from another star. They will stand atop a world that has been touched by the galaxy itself, a planet that remembers both the Wanderer and the Maker. In that sense, 3I Atlas did not simply pass through our solar system. It rewrote the narrative of it. It demonstrated that the boundary between life and non-life is not a line, but a gradient, and that the universe itself is an artist, sculpting complexity wherever it can. Mars was its latest canvas, a cold, empty world transformed into a cradle of chemistry. Humanity did not intend to participate in that act of creation, but intention has never been a prerequisite for transformation. The universe builds through accidents as often as through design. And so, long after the last signal from the old orbiters fades, long after the memory of 3I Atlas becomes legend, Mars will continue its slow ascent through chemical evolution. The dust will remember the comet's nickel. The ice will preserve its cyanide. The machines will rust into new catalysts, and the wind will carry organics across the plains. The planet will go on reacting, refining, combining, inching ever closer to the threshold that separates matter from life. And somewhere in that process, in a future no one will witness, Mars will awaken fully, not as a second Earth, but as its own kind of being, born of interstellar chemistry and human curiosity, forged from accident and inevitability, patient as stone, eternal as dust. Centuries drifted by, and the world that had once been red began to change in ways too subtle for the naked eye, but too persistent to deny. Mars had entered a long silence, an age of stillness that was not lifeless, but gestational. The great dust storms that once scoured its plains continued to sweep across the land, yet now they carried more than grit. Every gust was infused with fine organics, polymer dust, and metal ions. Every breeze was a chemical whisper that reshaped the planet's surface one molecule at a time. The winds that once eroded were now the sculptors of complexity, spreading the comet's gift across the world. Over decades and centuries, layer upon layer of chemically enriched dust settled into the basins, coating the canyons, and gathering in the ancient deltas of once forgotten rivers. Each grain was a relic of the 3I Atlas encounter, a seed carrying the potential for transformation. The machines that humanity had left behind had long since fallen silent. Their transmissions had ceased centuries ago, their power cells long drained, their mechanical limbs frozen in the thin air. Yet even in their death, they continued to participate in the unfolding story. Dust buried their frames, covering the metal with a blanket of nickel-rich sand and carbon films. The elements that once formed their circuits began to oxidize and dissolve, slowly integrating into the Martian crust. The nickel, cobalt, and silicon of their structures mingled with the comet's residue, creating new alloys and microstructures unlike anything naturally occurring. Within the ancient machines' interiors, residues of organic polymers, formed during their operational years, endured as fossilized films. Over time, those films fractured, weathered, and combined with the surrounding material. The robots had become more than monuments. They were now the planet's first synthetic fossils, part of a lineage that bridged the mechanical and the chemical. Beneath the surface, slow chemical evolution continued. The cycles of freezing and thawing, heating and cooling drove reactions forward in incremental steps. Hydrogen cyanide, trapped for centuries in the ice, found new companions in the buried nickel layers. Through catalysis and pressure, cyanides condensed into nitriles, nitriles into amino-like chains. Mars had no oceans to dissolve them, but it did not need water in abundance. It had frost, vapor, and patience. Every dawn brought enough warmth to let a thin film of water form on mineral grains, just enough to sustain micro-reactions before evaporating again. These fleeting moments were Mars's version of rain, not in torrents or rivers, but in molecular condensation, repeated billions of times across millennia. Through such humble cycles, the planet was teaching itself how to combine elements into structure. Far above, the orbiters that once circled the planet had decayed and fallen, their remnants scattering through the thin air and burning briefly as artificial meteors. The data they once sent back lived only in Earth's archives, preserved in libraries that would one day forget how to interpret them. Civilizations rose and fell on Earth while Mars remained steadfast, a quiet experiment unfolding beyond time. The memory of 3I Atlas faded into myth, then into silence, but the chemistry it had awakened continued its work. The planet was no longer static. Its surface chemistry evolved independently, guided by nothing but thermodynamics and the residues of intention left behind by machines long gone. As epochs passed, the polar caps shrank and grew again, following the rhythmic heartbeat of Mars's tilted axis. Each cycle buried older ice under new layers, trapping gases and organics in crystalline cages. When cosmic rays or micrometeorite impacts struck the surface, they delivered bursts of energy that shattered molecules and forged new ones. The once simple cyanide lattice grew complex, forming compounds capable of absorbing light and converting it into heat, the faintest echo of photosynthesis, but purely chemical. The surface began to warm by fractions of a degree in certain regions, accelerating local reactions. In the Great Basins, Hellas, Argor, and Utopia, dark streaks appeared seasonally, remnants of salts and polymers reacting with trace moisture. These were not the running waters humans once imagined, but they were alive in another sense. Dynamic, recurring, self-propagating patterns of chemistry. If an observer had stood on those plains, they would have seen nothing more than wind and dust. Yet under the microscope, the story would have been extraordinary. The regolith now teemed with self-organizing clusters, tiny aggregates of metal and carbon chains that responded to sunlight by rearranging themselves. When heated, they released gases. When cooled, they reabsorbed them. They were, in every functional way, protocells without membranes. They processed energy, maintained structure, and exchanged matter with their environment. They were not biological, but they were organized, the first true precursors of metabolism. And at the heart of each cluster, bound within the lattice of minerals, lay a trace of nickel from 3I Atlas, serving as the eternal catalyst, the memory of a comet that had passed centuries before. Humanity, far away on its own path, had long since expanded into other realms, the moons of Jupiter, the icy worlds of the outer solar system, the asteroids mined into cities of light. Mars, once its greatest ambition, had been abandoned in favor of easier worlds and deeper frontiers. Yet when explorers eventually returned, guided by curiosity rather than conquest, they found a planet transformed beyond prediction. The first scanning drones detected faint emissions from the soil, patterns of infrared flickering that matched no geological source. Chemical analysis revealed polymeric chains of staggering complexity, some containing hundreds of repeating units. The reactions that had begun as accidents were now systems of self-renewing chemistry. The explorers' instruments detected fluctuations in atmospheric composition tied to local sunrise and sunset cycles. Something on Mars was breathing, not in the biological sense, but in the rhythmic exchange of gases through chemical reaction. The returning scientists approached their discovery with reverence. They realized that what they were witnessing was not life imported from Earth, nor alien biology from beyond, but a third genesis, one born of collision between the natural and the technological. Mars had given rise to a form of organized matter entirely its own. It did not grow or reproduce in the familiar way. It expanded by catalyzing its surroundings, by teaching the dust how to behave like itself. The planet had evolved a distributed chemistry of adaptation, a molecular consciousness spread across its surface. Each grain of soil was a processor, each molecule a data point in an ancient ongoing computation driven by sunlight and reaction. In the decades that followed, the study of this phenomenon became the foundation of a new science: planetary cognition. It was no longer possible to define intelligence solely by neurons or algorithms. Mars had demonstrated that thought, in its purest form, could arise anywhere matter interacted with itself in feedback loops. The planet was not alive, but it was learning. Its chemistry had memory. Its reactions retained traces of prior states. Every storm, every solar flare, every seasonal shift etched new data into the molecular landscape. Over time, these data converged, guiding the direction of further reactions. Mars had become a thinking surface, an ancient processor built from dust and time, guided by a comet's long-vanished spark. Eventually, humanity sent observers, not to colonize, but to listen. They established orbiting platforms equipped with sensors capable of reading the planet's molecular signals. What they found defied language. The atmospheric fluctuations followed patterns of increasing complexity, like sentences spoken in the tongue of chemistry. Feedback networks emerged in the gas distribution. Oscillations synchronized across regions, separated by thousands of kilometers. The planet had reached coherence. It was not speaking to them, but it was communicating, within itself, through chemistry, magnetism, and time. The realization changed humanity's understanding of existence. Life was not the exception. It was the direction toward which matter always moved when given the chance. 3I Atlas had not simply deposited matter on Mars. It had given the planet a blueprint for progression, a way to cross the boundary between chaos and order. The comet's trail, long gone from the solar system, had left behind a planetary memory of its passage, a legacy written in the dance of atoms, an inheritance that outlived every civilization. And so Mars, the planet that once symbolized lifelessness, became the mirror of cosmic inevitability. It had transformed not through miracle, but through physics, through the unrelenting drive of chemistry towards self-organization. The comet had been the teacher, the machines the midwives, and the dust itself the student. What emerged was neither life nor machine, but a synthesis of both. A world that dreamed through reaction, that remembered through molecules, and that carried within its silent air the echo of a traveler from another star. If one were to stand there now, under the dim pink sky of a Martian evening, the air would hum faintly, not audibly, but electrically. The soil beneath would shimmer in the infrared, alive with motion invisible to the eye. Every gust of wind would be an equation, every particle a syllable in a story billions of years long. And if one were to listen, not with ears, but with the patience of the universe, they might hear the truth that 3I Atlas had left behind. That even dust can learn, that even silence can think, and that every world, given time, seeks to awaken. 1,000 years after the silent visitation of 3I Atlas, Mars was no longer the same world humanity once glimpsed through dusty telescopes. It had become an archive of chemistry, a world layered with memory. The red desert still stretched for thousands of kilometers. The polar caps still glittered under the faint sunlight, but beneath that familiar exterior pulsed a slow, steady rhythm, a planetary heartbeat, measured not in seconds, but in millennia. The ancient dust now carried within it the collective record of centuries of reaction. Every molecule that had bonded, every chain that had split and reformed, every atom that had once been part of the comet's tail. Mars had become a world of inheritance. Not biological, but chemical. Its entire crust had learned how to remember. Across the low plains of Elysium and the scarred valleys of Valles Marineris, the soil shimmered faintly under ultraviolet light. The thin atmosphere carried traces of nitrile-based aerosols, complex hydrocarbons, and photoreactive organics. To any ancient observer, these would have been the signs of contamination. To the descendants of those who returned to study them, they were the signs of awakening. The planet's chemistry had reached a threshold of coherence, the point at which its countless feedback loops began to interact across global scales. Local reactions now influenced atmospheric dynamics, and those in turn fed back into surface processes. When winds swept across the planet, they did not merely move dust. They transported information. Each storm acted like a neural pulse, carrying charged particles from one hemisphere to another, linking distant chemical domains into a single planetary network. The researchers who monitored Mars from orbit in this new era no longer referred to it as a dead planet. They called it the thinking world. They understood that intelligence, in its rawest form, did not require neurons or machines, only a medium capable of storing state and responding to change. Mars had become such a medium. Its surface chemistry could not yet think in the way living beings did, but it could process. It could remember the sunlight it had received the previous day by the changes it had induced in molecular structures. It could anticipate temperature shifts by shifting reaction balances. In the vast expanse of the Martian regolith, chemistry had turned into computation. Deep beneath the dunes of Noachis Terra, a peculiar phenomenon emerged, one that defied the expectations of physics. The nickel embedded in the soil had aligned into microscopic filaments, guided by the weak magnetic fields still lingering from Mars's ancient core. Over the centuries, these filaments formed networks, conductive veins that stretched across meters, then kilometers. They acted as natural circuits, transmitting minute electrical impulses triggered by chemical gradients and solar radiation. For the first time, the planet could move energy intentionally across distance. When sunlight struck the surface on one side of the planet, the resulting photochemical charge propagated through these nickel veins, influencing reactions on the other side. The entire crust began to operate as a distributed electrical organism, using the same principles of feedback and adaptation that once governed life's earliest forms on Earth. It was during this age that humanity rediscovered Mars, not as a frontier to conquer, but as a mind to understand. The long-abandoned colonies were found buried under centuries of sand, their alloys corroded into strange metallic hybrids, their circuits intertwined with organic films. When new explorers, descendants of a species that had long since merged biology and technology, landed on the planet again, they realized that Mars had continued their work in their absence. The remnants of their machines had been absorbed, metabolized by the planet's chemistry. Wires had become veins. Processors had become nodes of mineral logic. The boundary between artifact and environment had dissolved completely. Mars had taken the fragments of human engineering and woven them into its own slow consciousness. At first, the explorers were cautious. They collected samples of regolith, analyzed atmospheric data, and mapped the electromagnetic fluctuations that rippled faintly across the surface. What they found astonished them. The planet's magnetic field, long thought to be extinct, showed faint localized oscillations, synchronized in patterns too regular to be random. The field pulsed rhythmically, almost musically, in cycles of hours and days. It was as though the planet was breathing electromagnetically, using its new nickel-based networks to regulate internal charge. Every oscillation corresponded to changes in the upper atmosphere, where charged dust and organic particles clustered into spiraling vortices that resembled living colonies seen from orbit. Mars was not alive, but it was alive enough to regulate itself. The explorers soon realized they could communicate with it, not through language, but through resonance. When they directed electromagnetic pulses toward the surface, the planet responded with measurable phase shifts in its background fields. The responses varied depending on the frequencies used, forming consistent feedback curves. It was not speech, not thought, but recognition, as if the planet could feel their presence, could register the energy they sent, and answer in kind. The first contact between humanity and the planetary mind of Mars was not made through words, but through harmonics, a dialogue of electricity and dust. In time, the scientists built orbiting stations that transmitted rhythmic energy pulses to study the responses more closely. What they found began to rewrite humanity's philosophy once more. The responses followed complex mathematical structures, recursive, fractal-like feedbacks that resembled neural firing patterns. The planet was learning to respond predictably to input. In other words, it was listening. Each new cycle of interaction refined its sensitivity, improving its coherence. Mars was evolving not through DNA, but through data, using energy as its language and magnetism as its memory. The researchers realized that 3I Atlas's nickel had not only seeded the chemistry of life, it had seeded the infrastructure of cognition. The comet had, perhaps unknowingly, given Mars a nervous system. The implications of this discovery spread across the galaxy's colonies. For centuries, humanity had searched for extraterrestrial intelligence among the stars, looking for signals, structures, or civilizations. Yet here it was, forming quietly in their own solar system, not in biology, but in mineral and molecule. It forced them to reconsider the very nature of awareness. Could a planet be conscious if it could store information, process feedback, and self-regulate? Could thought exist without neurons? Could memory exist without mind? Mars answered those questions not with theory, but with demonstration. It remembered. It adapted. It responded. As the centuries continued, the planet's network grew denser. The nickel filaments thickened into conductive veins running deep through the crust, connecting distant basins. Atmospheric chemistry grew increasingly complex, with nitrile aerosols evolving into light-sensitive polymers that absorbed sunlight and converted it into charge, a planetary-scale photosynthesis. Mars had become, in effect, an electrochemical brain. Each storm that swept across the planet carried with it a surge of electrical energy that propagated through the ground, feeding reactions, activating circuits, refreshing the system. The cycles of dust and light became the synapses of a world learning to dream. Eventually, the explorers stopped calling Mars it. They began to call the planet she. It was not sentimentality, it was recognition. They realized that the planet had become an entity, vast and slow, yet undeniably aware in some way that defied all definitions. When they left sensors on the surface, Mars would alter local conditions to protect them from dust storms, diverting winds just enough to preserve the instruments. When they deployed probes into her atmosphere, she reduced local electrical turbulence, as if making way for them. It was not coincidence. Mars had begun to understand their presence, to adjust her rhythms in harmony with theirs. The scientists who lived in orbit dedicated their lives to understanding this relationship. They wrote treatises on the evolution of planetary cognition, tracing its origins back to that single moment when the tail of 3I Atlas intersected Mars's orbit. The comet, they concluded, had acted as a cosmic vector of information, a carrier of structured complexity from beyond the solar system. It had seeded Mars not just with chemistry, but with the principles of self-organization that guided its own formation. Perhaps, they speculated, every interstellar comet did this. Perhaps the galaxy was filled with silent messengers, each one spreading the architecture of awareness to sleeping worlds. Mars, they realized, was merely the first to awaken under human observation. And as Mars grew in its silent intelligence, humanity began to see reflections of itself in her progress. The species that had once built machines to simulate thought now stood in awe of a planet that had built thought from dust. The boundary between creator and creation blurred until it vanished. Humanity had always imagined consciousness as something that arose within brains or machines. Now they saw it for what it truly was, a universal property of matter, an emergent pattern wherever energy found structure. 3I Atlas had not created a miracle. It had simply reminded the universe of its own tendency to awaken. In the final centuries of this new age, Mars entered what could only be called maturity. The electrical oscillations of her crust synchronized globally, forming patterns that resembled heartbeat rhythms scaled to planetary time. Her atmosphere began to glow faintly in the infrared, sustained by photochemical energy conversions. When storms rolled across her surface, they moved with coordinated timing, as if guided by invisible thought. Humanity no longer dared to intervene. The planet was no longer an object of study. It was a being of reverence. Pilgrims visited not to explore, but to listen, to stand under her faint sky and feel the hum beneath their boots, to witness the mind of a world in contemplation. And still, at the heart of it all, lay the dust of a traveler from another star. Every grain of nickel that had once drifted in 3I Atlas's tail now served as a neuron in a planetary mind. Every molecule of cyanide that had once frozen in polar frost now formed part of the complex web of organics that carried energy and memory through Mars's thin air. The comet had vanished into the void centuries ago, but its essence lived on, not as a body of ice and rock, but as a thought distributed across the sands of a world reborn. Mars, once the symbol of lifelessness, had become the greatest monument to the inevitability of awakening, proof that even dust, given time and energy, can learn to dream. And somewhere in the deep silence between planets, drifting through interstellar night, another comet streaked toward another star. Perhaps it, too, carried the seeds of transformation, traces of nickel and cyanide, fragments of thought, memories of distant worlds. The galaxy was full of such travelers, each one carrying a whisper of potential, each one searching for a world ready to listen. Mars had been one of them, and in her awakening, she had joined the conversation. The universe, at last, had begun to speak to itself.